Good afternoon and welcome to today's seminar. My name is Melanie Zauscher and I'm a staff member at the California Board. Is there an echo? Just me. Okay. So before we get started, a couple housekeeping items. The restrooms are if you go out this door to the back and then to the left. And unfortunate circumstance that a fire alarm goes off, please calmly follow CARB staff down the stairs, out the exit, across the street to the park. All right, so I'm the contract manager for this study, and it gives me great pleasure that the contract is complete after many years of hard work. And thank you all for joining us today so you can learn about the very interesting findings we'll hear today. For those of you online, please email your questions as soon as you think of them to the address listed on your screen. That way we have plenty of time to ensure your questions are also asked. Before we get started with the actual presentation, I wanted to provide some context for the study. The study today that we're going to hear about is an important component of our broader low-carbon transportation research, which supports our efforts to reduce transportation emissions to help meet California's climate and air quality goals, create healthier communities, and work towards equality and access to clean transportation. For more information on other research projects in this area, please visit our low-carbon transportation research website listed on this slide. As some of you know, California has set a goal of having 1.5 million zero-emission vehicles and plug-in hybrid electric vehicles by 2025 and 5 million by 2030. These goals were set to help meet California's climate and air quality goals. Zero-emission vehicles are those that produce no tailpipe emissions and include battery electric vehicles and fuel cell electric vehicles. Plug-in hybrid electric vehicles use both a gasoline engine and a battery to power the vehicle. To help accelerate the zero-emission vehicle market, California requires, through the Advanced Clean Car regulation, that automakers either produce and sell zero-emission vehicles or buy credits. Because this technology is still being developed and can be expensive, California also provides rebates to consumers of new zero-emission vehicles and plug-in hybrid electric vehicles. The actual emission benefits of these vehicles depend on how they are driven and charged and the household composition. For instance, a household with multiple vehicles, one of those being, for example, a battery electric vehicle and another being a large truck, would be very different from the emissions of a household that only has one car, a plug-in hybrid electric vehicle. Emissions are also highly dependent on how the electricity and hydrogen is made, which for the electricity depends on what time of day the vehicle is charged. At the January 2012 hearing, CARB's board resolved to study consumers' actual usage of zero-emission vehicles. Hence this study. Results from this study have already been used to inform Advanced Clean Cars midterm review in 2017 and will inform the next iteration of the program. Some of the main research questions the study was designed to answer include, but are not limited to, are battery electric and plug-in hybrid electric vehicles driven differently between themselves and in comparison with an internal combustion engine vehicle? Within each category, how does the vehicle's electric range impact its usage? How and where are these vehicles refueled? Also, within the household context specifically, how are these vehicles used? Are they only used for short trips or are they also used for long trips? This study is a very complex study and generated a lot of data. Specifically, the researchers have surveyed more than 11,000 electric vehicle owners, and from these, a subset of 200 households were selected to have their vehicles logged for about a year. And each logger was collecting data in the order of 1 to 10 seconds every time the car was operating for multiple parameters. Today, we will hear results from the study, which focused on the electric vehicles available in 2015 through 2017. There is a follow-up study by the same research team following the same methodology that is focused on the next generation of zero-emission vehicles. In about a year or so, we will hear results from that study. So stay tuned. Today's presenter will be Dr. Gil Tal, the director for the aptly named Plug-in Hybrid and Electric Vehicle Research Center at the University of California, Davis. He is a leading expert on electric vehicle travel behavior, as well as understanding the role that incentives and infrastructure play in the electric vehicle market. He also researches the electrification of new mobility services. Dr. Tal obtained his PhD in transportation technology and policy from UC Davis. Due to time constraints, Dr. Tal is unable to present all the interesting findings from this study. As I said, there's a lot of data and a lot of very interesting things that can be looked at. Of course, we're not paying for the analysis of all this data, but nonetheless, there's a lot of interesting stuff in there. And you too can read the results of the study and the report. Once it is available on our website, we have to make it ADA compliant before we post it and hope to do that very soon. I also want to acknowledge the California Energy Commission for co-funding this study. And finally, I'd like to thank the whole research team because this was not an easy project. There was lots of roadblocks and detours, but yet here we are finally completing the study, and we appreciate all the effort that was put into it, so thank you. With that, I'd like to invite Dr. Tal to present his presentation, and then if you have any more questions about the general background, here are some resources.
Thank you, Melanie. Thank you for the opportunity to present this walk. And I have to add to what Melanie said, that it was a very complicated project, a very complicated data collection project. For a while, we were not even sure that we will have any real results coming on the other end. And without very strong support from CARB staff over the years, on the procurement of these loggers, on pushing the data and helping building it from different pieces, it wouldn't have happened. And I think that what I will present today is only the first part of a huge data set. We're still collecting data today that will be useful for many more things that in the future. So without continuous support over the years, there is no chance that we would have done it ourselves. On our side, it was also a large team. If you are familiar with the names, you know that many of them already moved to different positions in other places. But we started testing different loggers in 2013, just to see if we can even collect the data. And in 2015, we had this contract when we kind of figured out that we can. And in 2017, we were collecting data, but not sure that we know how to read the data. But by now, I think that we have a very good system there. So I will talk a little bit more about the background and motivation, but Melanie was kind of giving us good overview and a little bit even more on the methods and design. And then we will go to talk about some results. How much people are driving different full electric and plug-in hybrid, how they charge these cars. What do we know about the utility factor of plug-in hybrids, the share of electric miles that they are doing, and what do we know about the household level? If they drive 2 or 3 cars, what do we know about that? Then, after collecting so much data from the cars, we went back to the drivers and talked with them about why they are doing things that we're doing. And as usual, when you send Ken Coroni to do good interviews, you come up with surprising results, and I picked just a few of them. And the last part will be about PHEVs and engine starts, which is more related to cold starts and to criteria pollutions, a little bit different topic that we added to this project. The conclusions will be just few of a much larger sets of conclusions that we can talk about. So I don't think I need to repeat this one, so maybe we can save time, but the idea is knowing how these cars actually behave on the road, in a household, not on the dyno, not doing some simulation, but actually with real people for a full year on the road, collecting second by second, more or less, data, collecting charging data, knowing where they are and everything about them for a full year. Now, I have to admit that with all the support from CARB, in the end, this is a data collection project. this project haven't had any large research or analysis component to it. Most of the time and the people involved in it were into data collection. We are lucky to have a lot of students that are interested in more than that and need their dissertation, and also we are, as researchers, always push forward. So we already have many papers that are much deeper analysis published and under review, and we will have more. And we are using this data to go after more projects and more opportunities. But what I will present today is just scraping the surface of how much deeper we can go with the results. So we started with a recruitment survey. We called it a recruitment survey. It was a 40-minute survey on average. So we asked them everything under the sun. How do they travel? Why they decided to buy this car? Where do they live? What's their income? Everything we could to ask them. And we kept doing it from 2015 till 2017. We have 11,000 complete surveys. We keep doing it today with newer ones so we can compare it. And from this group, we invited everyone at the end of the survey. We asked them, are you willing to participate in the logger study? And if they check this box, we selected the people for the next group. The next group contained 264 households in 4 waves. We were trying to recycle the loggers. So a logger was used for a full year. Then we uninstall it from one household, install it to a new household in order to save the cost of buying a new set of loggers. And we try to collect all the parameters on the vehicle to be able to estimate energy consumption of the vehicles. Battery state of charge, fuel level, not really walked, speed, RPM, location, charging level in kilowatt hours, etc. At the same time, we install loggers on all the ICEs in the household, almost all the ICEs in the household, and we're trying to know how much they were being used, what's the energy use of the ICEs in the household, and we did interviews for a subset of those. All of this data was streaming into our servers from the vendor in different ways. The data was changing all the time, and the biggest challenge was to make sense of the data. Each car had different data stream, each model, and also the loggers were changing over the years, and the cars were changing over the years. So we had a continuous change of the data was streaming into, and we still have a continuous change of the data streaming into our servers. We also have a continuous learning curve because the vendors don't always know what they are streaming to us. Their understanding of what the logger is streaming is not always much better than ours, so we are learning together while the data is coming in. As I said, it's a continuous learning experience. And cars change over the years. We started with plug-in Priuses that are not on the market anymore, 11-mile range. The numbers here are the range of the car. Ford Fusions and C-Max plug-in hybrids with 20 miles range, the first generation Volt with 36-mile range, first generation Leaf on average 80-mile range, depends on what year you measure it. And today we're still collecting data from the second generation Volts, from the newer Leafs, Tesla's different size of batteries. We spend a lot of time and effort to collect data from the i3 Rex with the range extender, but the data was not usable. So all of the effort on these cars were, I will not be able to present it. Prius Prime, the second generation plug-in Prius. The Pacifica plug-in hybrid, which is a great, the first full-size car, not a sedan. The Bolt, and the fuel cell Mirai. So all of these cars we are collecting data today. So as I said, we had 14,000 surveys that finish, but 7,800 actually were putting in emails that we can recruit them, the right vehicle, the right time, and so on. Not every question in the survey everyone been asked and answered. It depends on the logic of the survey, depends on the topic. So you will see the sample size changing over my slides, and that's because of that. Also, not all the cars were logged, especially not all the ICEs. You have to install these small loggers into the OBD port in the car. Not in every car you can drive when you have the logger in the port. Some cars you will hit it with your knee, some cars it was not designed for that, and some OEMs are doing their best to prevent it from happening. So because of that, the technical issue, and because of a big uncertainty that we were totally not taking into account when bidding on this project, we had to contact these households at least twice, sometimes 3 times over the year that we were collecting data. We recruited them. They said, yes, we are willing to install loggers. At the first, we had to travel to their household and install these loggers. They had a different antenna. We had to put wires under the trims and all that, all over California, from San Diego to Humboldt County. And our hope was that a year later, we will visit them again and uninstall the logger, give them the gift card, and say thank you. But people are changing their workplace, moving to a new house, having an accident with the car, having a new car, getting divorced, moving to Hawaii, and everything under the sun. And we end up traveling to 60% of the households more than once, sometimes twice, losing some of the loggers that disappear with households who stop talking to us, and so on. We were pretty naive when we started. I already talked a little bit about the challenges with the logger data. The biggest challenge was to put it on a time series database and to figure out, again, it took us long, to figure out, I will not talk about all the different challenges, but I will talk about one. Every time that any of the data points were changing, we were receiving from the data vendor a new set of data for all the other factors. Some of it was just a repeat. Some of it was new read. We had no idea what is a new read and what is a repeat. So our data is not perfect, and we had to do a lot of jumping through hoops trying to figure out what do we have there. For analyzing energy consumption, I think it's no problem at all. For analyzing power, we are getting into more trouble because then you need to have instant power and combine the different things. And of course, missing data, changing file, and so on. Let's talk a little bit about the sample. Yes, people who have, especially 2015 electric cars or older, high income. But I think we did a very good job. The orange one is the people we logged. The blue one is the 14,000 or 11,000 people survey. And we were trying to match these two, trying to match them by sociodemographic. We also tried to match it by regions. We were doing everything from Southern California to Humboldt County, as I said. So let's talk about VMT. This slide is about 4 different data sets. And I created these slides after reading a paper saying EV owners are not driving their cars, so we're not getting the benefits we are expecting. This paper was actually based on the National Household Travel Survey and the California subset, which is the blue bars. And the blue bars are, it was published in 2017. The data collection was 2015-16, but the newest electric cars they had in their sample were 2014-13 and older. So it was very early leaf owners. And as you can see, for BEV, short-range BEV, they show about 7,000 miles a year. But when we looked on our survey and we asked people, what's your odometer reading, what months you are taking ownership of the car, and also on the log data, we see that short-range BEVs did more than 10,000 miles. And if we look on long-range BEVs, they're doing much more. Look at ICEs and PHEVs, it's very similar. It's pretty clear that PHEVs are doing more miles than every other car in our sample, and that's a good topic to more research. But that's just a background on that. When we look at the cars we logged, and each bar here is one household, it's interesting to see that we have on the 24 kilowatt hour Leaf, this very short range blue one, some people who did low annual average daily VMT, 12 to 14. On the other hand, we have people who did 50 miles a day, similar to the Leaf 30, the Teslas, and the Tesla 80 plus, or 80 to 100 and 60 to 80. Where the difference starts is this very long few households that do a lot of miles. Up to about 80%, it's all the same. It's about how much miles they need. But some Tesla households, some long-range Leaf households are doing these very long miles, and that's where the bar change. Another way to look at it is here. So this is daily miles by different bins. The bottom one is household, how many of their days they did 0 to 10 miles. It's between 3 to 4% of the short-range Leaf did less than 10 miles a day. Actually, with the Tesla, you see that more than 10% of the days they did less than 10 miles. They were probably on the Riviera for a vacation or something. And if you look at the orange, 20 miles a day, you see that it's around 20% plus minus of the days that they were doing less than 20 miles a day. Again, where we see the difference is the dark blue on the right, the green on the right, where you have the long-range car, you can do the last 10% of the day, the last 20% of the days on a very long trips. But up to about 60 to 70% of the days, all the cars from 24 kilowatt hours to 100 kilowatt hours are doing more or less the same mileage. So the BEV is allowing them to do this extra, very long days. And later I will show in the analysis how far from home they are and where do they charge when they do these very long travel days. So let's talk a little bit about charging their BEVs. We have surveys, we have log data, we have data that is not from this study, from the infrastructure. And I was just wanted to put it all together into a set of numbers. Sometimes we count it by the number of charging events, sometimes we count it by kilowatt hours, sometimes we count it by miles. Any different way you look at it, about 80% of charging is based at home or overnight charging. Maybe the right way to say it is overnight charging. About, again, you see it's not a one number here, 30 to 50%, it's walk, very little public DC fast, and even less level 2 that is not walk or home. And this is, whatever way you look at it, that's kind of the big pyramid. For example, on our survey, 53% of the survey takers were not using any charger except from home in the last months. We asked you, the last 30 days, today is this date, last 30 days, have you used any other charger? No, home only, 53%. If you add to it 16% who did home and walk and 13% who did home and other, which is usually Tesla drivers who have free fast charger and they stop, when they're doing the shopping for a free charger. Home is a very dominated location. We still have on our survey this 4% that do, 8%, the orange sliver there, who are doing walk only. It's cheap, it's enough for them, they're doing walk only. And we have a small group, I think that's the 4%, who are doing other only. So we already have, 2017, 12% who are not plugging in at home. I have to admit that in 2017, we were not smart enough to ask them. So I will show a slide now from 2018. So it's not the same group, just to make sure that you know it. On the 2018 survey, I did ask these guys who are not plugging in at home, can you? Okay, you're not doing it, but can you do it if you need to? And if you look at all the way to the right side, you have people who already have a level 2 charger at home. 15% of the BEV owners who are not using home chargers have a level 2 charger at home. And another 40% of the BEV owners have a level 1 capability at home. So it's already, we are at 55% of the people who are not using home chargers can do it. And we need to know that a lot of the charging behavior, one of the papers that I list there, is about the impact of price of home electricity, price and availability of workplace chargers, and so on the behavior, people just substitute. It's not that they cannot use home chargers, they just have a cheaper option, at least half of them. Still, we have half. Depends on how do you count it. I don't think that extension cord is a valid option. So we have about half that cannot charge at home. So today, on our new survey, we have about 5 or 6% of the PEV owners that cannot plug in at home. That's also an important point to make. Another important point to make about charging behavior is fast chargers. In this point, actually, is the white space above the bars that I'm always focusing on. 60% of the Leaf and Tesla drivers, they have it for free, did not use a fast charger in the last months, in the last 30 days. Everyone is using it at least once or twice. You know, they bought a new car, they plug it in, it's fun, thank you. But 60% did not. And about 80 to 90% of the Bolt, VW Golf, and i3s were not using it. So for the last months before the survey, they were not visiting a fast charger even once. We have a small group who are using it. Most of our BEV owners are not using it. Again, on a different survey, different set of questions. Can you use one if you need to? Yes, many of them have the opportunity. They just don't have the need. They don't have the need. They have home chargers. They have usually a lot of time workplace chargers. And these chargers, they may use it once or twice a year, but not on a regular basis. How much electricity they take every time they plug in. That's not a surprise. This is all full electric cars. If they use level 1, the limiting factor is time. And then on average, it's 6, 7 kilowatt hours on a charging event. Doesn't matter what the size of the battery is, the limiting factor is charging time, and that's the maximum we see. When we go to a level 2, we start to see the impact of the battery size, and we have 8 on the 24 kilowatt hour battery Leaf, 12 or 13 with the Bolt, and when a Tesla is plugging in to a level 2, it's on average 21, 24 kilowatt hour charging event. Now, we will go back to it, but it's not because they travel more. It's also because they travel more, but not just that. The other reason is because they plug in less times. When you have longer range, there are two things happening. When you have longer range, you drive more, but you have longer range, you just not need to do it every day. And the higher kilowatt hour charging events are a substitute for frequency. And a similar thing you can see with DC fast chargers. I have to admit that a 9.3 or even a 15 kilowatt hour charging event on a DC fast charger seems to me like a waste of a very expensive piece of equipment, the fast chargers. But when we go to a 24, 29, or even 38 kilowatt hours, it starts to make sense. So when we had this very short range BEVs around, and they can charge only to 80%, and they arrived with 20% because they really don't want to take a risk. It was not a great deal, but when we have longer range BEVs, we make more sense. So as I said, frequency. This is the frequency of charging events by day. So did you charge in this day or not? Sometimes it's twice a day, but it's still, did you charge in this day or not over the year that we collected data from this car? So over a year of data collection, we don't have even one car that was plugged in every day. Pretty kind of obvious, people are not at home all day. We do have this one Tesla and the green top there that was almost every day plugged in his car. But if you look on average, we have a Leaf, the short range Leaf are clustered at the top on the 60, 70%. They have to plug in almost every day. That's the cluster. And when you go to longer range cars, it's much more spread. Some people plug in every 4 or 5 days. Some people doing it more, but it's much more spread. It's much more about their availability and need than the range of the car. And when we install, how many chargers do we need for X number of cars? That's kind of part of the answer. Depends on how often they're plugging in and where. And with BEVs, it's the energy mostly come from level 2. Level 1 is the bottom blue there. It was important for some of our short-range lifts, 24 and 30 kilowatt hours. But most of the energy for Teslas and for short-range lifts are coming from level 2. We can also see it in bolts, just the same with the new data. And fast chargers, because they're free, in some households they're being used quite often. So for the Teslas, it's about 15 to 20% of the energy. And for the Leaf 30, it was 25% of the energy. Why for the Leaf 30 it was 25% of the energy? Because when we logged them, the Leaf 24 kilowatt hours were older and were already out of the free charge for charge. And the Leaf 30 kilowatt hours were still under the free charge for charge, so they were doing more DC fast chargers. It's not about the vehicle, it's not about the technology, it's about this group still had free chargers, this group already had to pay for it. That's a behavior thing. And when they plug in, when do they plug in? It's a very important question for the energy side, for the energy sector, for modeling, GAG, and so on. There is, I think, 2 important points here, or 3. The blue 8 to 9 a.m. peak, that's workplace charging. About 5% of the charging events happen when people show up at work. Then we have this dip, and at 4 p.m., we're starting to see this growth when people start driving home, and it's keep growing all the way to midnight. I was expecting to see a PM peak, same as we see at 5 p.m. when people drive back home. We don't see a PM peak. And I've seen some other data sets that are not showing this PM peak. But we do see a huge peak at midnight. And this is timers. About 12%, 10 to 12% of the sample are using timer. So we have a huge peak now at midnight. It may or may not be a problem that we want to fix, but we do have a midnight peak today. And as I promised, where do they plug in? So this figure behind me is taking out everyone who plug in at home. So everything that happened less than a mile from home, this is the GPS location. We assume that it's a home and it's just a noise, and we clean it up. These are the charging events that are more than 1 mile from home. Level 1, that's the green, have a peak at about 10 to 15 miles from home. That's the workplace charging on level 1. And then you can see DC fast, 25% happen 1 to 5 miles from home. 25% of the DC fast charging events happen less than 5 miles from home. And we have another kind of like less than 20 miles from home. And it's all kind of going down. Doesn't matter what car it is. It's including Leafs and Teslas and everything. And then when we go the far end of more than 100 miles, we don't have a lot of level 2s more than 100 miles from home. It's about 2 to 3%. We have a lot of DC fast. Well, about 8%, what is it? About 8% of the charging events happens more than 100 miles from. And about 10% of the level 1 charging events that are not happening at home, not excluding home, are happening really, really far. It's usually at your aunt's home or when you're visiting grandma or something like that when you plug into level 1, or at the garage of the hotel that doesn't have a charger when you plug in on level 1. So actually, I was surprised that level 1s happens at this far distance more than DC fast charger events. Now, we had this question of corridor charging, how much people are charging on their way. And we decided to split between home location and overnight location. So the top one is distance from where you started your day. And the bottom line, bottom figure, is the distance from your home. Exactly the opposite, yeah. Home will be at the top, and yeah, home at the top, and where you started the day at the bottom. If you want to see kind of one point where the difference is, look at the more than 100 mile. When you look at more than 100 miles from home, it's about 20% of the fast charging events for a Tesla. But if you look distance from where you started the day, it's only about 10%, 12%. What's happening there is that we have a lot of road trips when people are doing this long trip, let's say from here to Vegas, then they stay there for a couple of days, then they drive back. So they are plugging in away from home again and again, but it's not because they are on a corridor on the way from point A to point B, it's because they are at their destination. Another option for that we have seen quite a lot on our Tesla drivers, they have a cabin somewhere. They have a second house, they have a summer house, they have, you know, a retreat. They are there for a couple of days. They are driving around, they're far away from home, but they're not using more than level 1, and then they drive back. Looking at that, we kind of can figure out that the corridor, the trips, the fast charging that happens on the way to a long trips is less than 10% of the fast charging events. When we just look at compared to where you started the day, or around 10% of the charging events for the Teslas. The flat line there, no pulse line, is the more than 100 mile for a Leaf. It's just much closer to zero than anything else. I think that it will be different with the Bolt when we'll present that. So yeah, that's kind of a very shallow analysis of BEV charging behavior. And let's talk a little bit about PHEVs. They have the option not to plug in. And PHEVs, you know, all the different weekdays, weekends, level 1, level 2, it's much more subtle differences. We are starting here from level 1 in weekdays, level 1 at weekends, level 2 in weekdays, and level 2 at weekends, and you don't see a big difference. It's all between, you know, 5 to 8 kilowatt hours for the long batteries on average, 1 to 3, 1 to 2.5 for the short range. And in general, I think that there is not much need for faster level 2 chargers for these cars if they are between 4 to 18 kilowatt hours. And not surprising that level 1 is very dominant for short-range PHEVs. The plug-in Priuses, the C-Max, most of the charging sessions, charging events are level 1. Even for the Volts, we have quite a lot of charging sessions that are level 1. And if a Volt driver or any plug-in hybrid driver asks me today, do I need a level 2 charger? I'm saying maybe. You don't know before you try. Try level 1. If you can get more miles with installing level 2, then go for it. But not everyone needs it. And then, you know, what with the PHEV performance? Are they actually carrying their weight? They got some money from the CVRP, from the federal government. Do we actually want them around? What's the EVMT, the electric vehicle mile travel? How much of their trips are zero vehicle mile travel, which means the engine didn't even start? And what's the utility factor, the share of electric miles out of the total miles that they're driving? It's a complicated story. It's a complicated story. The gray boxes are their total miles that each one of these cars was doing. As you can see, we have some C-Max Fusion that did about 2,000 miles a year, all the way to 28 or 35,000 miles a year, some 1 point up there. So if we talk about share of their electric mile, first we need to see how much they're driving. And then the red one is how much they were driving on gas. Yeah, so if you drive 30,000 miles a year, you will drive almost all of it on gas. It doesn't matter what kind of plug-in hybrid you have. The green is how much miles they did on electric. Very short-range plug-in Prius cannot do much. Even if they really try, it's a very small box at the left. And when you go for more range, you see a wider distribution and also more miles. But still, even with the long range, you have a really wide distribution. This is the distribution of the utility factor, the share of electric miles they are doing every year. And as you can see, it's almost everything between 0 and 1. So actually, on this figure, I would like to focus on the empty spaces, the two white spaces we have on this figure. The two white spaces, I think, are the important story. The white space above the plug-in Priuses say, doesn't matter what are you doing, how often you plug in your car, how little you drive in your car, you cannot get a lot of electric miles or a high utility factor out of a short-range plug-in hybrid. That's one part of the story. The right end of the story, the Volts, saying exactly the opposite thing. Now, this is a subset of people who plug in their car. So if you drive a Volt without plugging in your car ever, drive it as a hybrid, you are not in our story. But if you do plug in your car, and you're in our story, there is no way not to get some electric miles out of your car. There is no way. It's really, really hard to get less than 40% of your miles on electric when you drive a Chevy Volt. And we see it on different side of the story. So that's kind of very, very big picture. If you drive a very short-range car, and we have new short-range car coming into the market, mostly from European OEMs, you cannot get much electric miles. If you drive a long-range plug-in hybrids, it's really hard not to get at least 40% of your miles on electric if you're doing it right. And this is about your days. The blue one is how many of your days your engine didn't start. If you drive a plug-in Prius, it's correlated with the days you didn't drive much, maybe to the grocery store, not accelerating, really, really careful downhill. You can finish a day without the engine start. With the C-Max and the Fusion, the Ford, they were able to finish about 20% of the days without the engine starts. But with the two types of Volts we had, it's 55 and 63% of the days and without the engine starts. The gray bar, days that they had some of their miles on electric, some of their miles on gas. So they were driving further out of the range of the car. And that's kind of the adding to close to 100 for most of the cars. And the orange at the top is these days that they were driving, starting the day on gas, ending the day on gas. There had no electric miles on these days. Again, if you drive a Volt on our sample, you hardly have any days that are fully gas days. This is a behavior topic. They get to a place, and because they have this benefit from this car, they will look for a charger. While if you drive a plug-in Prius and you get to a place that you're out of home, you not always look for it, or a C-Max, you not always look for a charger. It's a behavior, it's not a technological story. So as I said, they can drive more than half the days on electric. So they have, if we look at days, they have 55 to 63% of the days as electric. So if we combine all these utility factor stories together, the gray one is what we were expecting them to do based on the SAE utility factor. The SAE utility factor assume one charging event every night. So you start a day with a fully charged battery, and the driving distribution based on the NHTS, how many miles a day they're doing. And based on that, we were expecting the plug-in Prius to do almost 30% of the miles on electric. We only get 15% on the cars we were logging. If we add to it the people that on the survey told us that they are driving on gas only and not plugging in, only 12% of the total miles of a plug-in Prius were electrified. The other 88% are pretty good hybrid miles, but not electrified. We still see a big difference with the C-Max, 45% expected, 33% measure, adding the people who are driving on gas only, 28%, that's our bottom line on this one. With the Volts, the differences are much lower, 66 versus 60. or 76 versus 64. Why we have these differences? We have 4 reasons. On the list of papers, I have a paper under review that kind of put what the percent of each reasons to the difference. Reason number 1, people drive more than what the utility factor was expecting them to do. If you do 30,000 miles a year, your utility factor will be half of what if you're doing 15,000 miles a year. Reason number 2, the efficiency of the cars is not as high as the utility factor was expecting because they are using 1 driving cycles and Californians are driving faster. Reason number 3 is that they are not plugging in as much as we expected. So we expected once a day, and they're doing less than that. Actually, on our sample, many of them are doing more than that. So it's kind of balancing it. And the last reason for the difference between the utility factor and what we see here is, what is the last one? We do have 4. So we have charging behavior, we have total miles, we have efficiency, and I can't remember what the 4th one. If I remember, I will come back to it. Okay, we talked car till now. Let's talk household for a second. But before we talk household, let's talk GHG for a second. Because utility factor and GHG is not the same. The green line is what we see on our log cars, what the utility factors of these cars. As I said, 12% for the Prius, about 32% for the C-Max, 60-something to the Volts, and big surprise, the utility factor for BEV is 1. All of their miles are on electric. But when we use the average grid numbers and we use the conversion from gasoline, it's not that bad to drive it on a hybrid. So a Prius, on average, on our data set, did 220 grams per mile. A Volt that had a lot of their miles on electric, 180, 170 grams per mile. And their full electrics, if it's a light, efficient Leaf, it's about 190. If it's a heavy Tesla, it's about 140. So the difference between a Tesla and a plug-in Prius that use the same electricity is between 220 and 140 grams per mile. It's still a big difference, but we have to remember that it's not just about EVMT. We have another factor that we need to put in. So households. Households, it's a mess. 220 households, it's 220 different stories. And we are trying to make some statistics here. Because they have different ICEs, they have different driving behavior and so on. Let's try to kind of put them all together. The 77 blue ones are 1 ICE, 1 plug-in hybrid. The 51 orange are 1 ICE, 1 BEV. The 47 gray are only 1 car household with a single plug-in hybrid. All the other there are another mixes of 3 cars or 2 PHEVs and so on. They're all there. That's the wrong one. I should have come up with much more simple. That's the utility factor of all of these different households I showed you, BEV combined household on one side and PHEV on the other. So on the left side, we have a Leaf 24 that have 2 ICEs, a Leaf 24 that have 1 ICE, and similar on the right. Let's just look at the big picture. Find this Leaf 30 with 1 ICE, 1 BEV. That's a very wide box with red numbers in it. So the utility factor of household with 1 Leaf, 1 ICE, between 0.2 to 0.8. The utility factor of a PHEV, any PHEV with 1 ICE, is more or less same, 0.1 lower, 0.2 lower. There is a lot of overlap between the utility factors. If you go to utility factors of longer range cars like the Tesla, again, I think that the important part here is the white space. There are no wide distribution anymore. They don't have a lot of lower end utility factor. They're all on the higher part. Well, for the PHEV, you always have this really wide distribution. Let's try to dig a little bit deeper. Another too busy one. The dotted red is your PEV utility factor. So you can see that's the one I already showed you before. You can see how it's grow for plug-in hybrid and then how it's 1 for BEVs. The dotted green is the utility factor of the household. And again, it's growing when you have more range PHEVs, and then when you have more range BEVs, it's keep going up. Another way to look at it is orange is electric miles in the household, gray is gasoline miles in a plug-in hybrid, and blue is gasoline miles in your ICE. So pretty clear, long-range BEV plus ICE get you more electric miles. That's pretty clear. What I'm not showing here is the GAG. Because if you drive a lot of your miles on the gray, you drive a very efficient car. If you drive on the blue, it's usually the household that have a Leaf. They didn't replace their Honda Pilot or their Ford Explorer with the Leaf. They got rid of their Prius, and they have a Leaf now. And they're still driving their Ford Explorer or Pilot or any of these big SUVs on their blue one. So to understand the GHG impact of a combination of BEV and ICE, we need to dig deeper. And the problem we have right now is actually each one of these cars have different utility factor, and we have different greenhouse gases emissions. And I decided not to present it today, but we will get to it. And there is a paper at work that you will be able to see in a couple of months. So a little bit about the interviews. Okay, now we know that we are all over the place, but can we learn why? I was very surprised from Ken's interviews to learn that I thought, okay, we do have a big problem in California or globally if people don't understand PEVs. But now I know that we have even bigger problem. People with PEVs, they get one and they think that they know all about it. And whatever they learn when they get the car, they stuck with their knowledge. They're not moving forward with it. If there are more chargers out there, we don't really know. We got to our habits and we stuck with our habits. The biggest problem, I think, is plug-in hybrids. If you drive a plug-in Prius, you think that all plug-in hybrids are a plug-in Prius. You don't really understand that a Volt is a totally different animal, that the engine will not start, that you drive actually on electric for 40 miles. You think that all plug-in hybrids are your car. If you drive a Volt, you think that the plug-in Prius is your car, and they can actually drive on electric. And you will recommend a friend or someone, hey, that's a pretty good car. I know, I'm driving a Volt. A huge gap in understanding whatever the people start with, that's where they are today. And that's how they operate based on this information and are not learning. When we were sure that they are with us, no, they are the year that they bought the car. I'm not sure what to do with it yet, but that's something we learned in the interviews. Now, that's pretty obvious, but it was very, very clear at the interviews. To get better EVMT, we have a short window after they purchase the car, when they learn how to operate it, how it works for them. And if they need an EVSE, that's the time to give them an EVSE. If they learn that they have a workplace charger, that's what they will do. And that's the window. The motivation to buy the car have a big impact on the way they drive the car. We interview a person who went to buy a plug-in hybrid. They offer him to show him how to plug it in, and he said, oh, no need. It's only for the sticker. So if that's what you're doing, you're not getting any miles. If you're driving if you care about the environment, if you try to save money, if you have infrastructure, if you have seen charger at work, you will get much bigger impact. There is, of course, always this balance between trying to sell as many cars as we want and trying to sell them to the right people. Now, I'm not saying that HOV sticker is a bad incentive. It's a very, very good incentive. But we see less of this impact of not plugging in if you drive a longer range PHEV. We see more of this impact if you drive a short range PHEV. And I think that we need to think about, incentivize chargers for the right households. Not for a short range PHEV, for the long range, for BEVs for sure. When we put more chargers, we get immediately more electric miles, immediately less greenhouse gases. Last topic that will be pretty fast is engine starts. The motivation here is cold starts are most of the criteria pollution. PHEVs also may have the problem of high power cold start when the engine starts not because the battery is empty, but the engine starts because the motor cannot supply enough power and you need the engine to kick in to help with the power. High power cold engine starts have much higher emissions. We don't have enough information from our loggers to pinpoint it, but we at least can give the big picture of if it may happen and under what conditions. To start, I'm going back to the slide I already showed, saying that if you drive a long-range PHEVs, you have no engine starts, cold, hot, warm, on more than half of your days. That's very good for criteria pollutions. If you can finish most of your days without engine starts, yeah, that's done. But if you do have the engine start, how many of these starts are cold? How many of these starts are warm or hot? So what we have here is the temperature at the first start, that's the blue, and then the temperature at the second and after starts at the trip, that's the red. So if we look at the C-Max and the Fusion on the left, 60% of the first starts happens in ambient temperature, about 50 to 100 degrees. Then we have this slope going up to 100. That's when the engine starts after it was walking a little bit earlier. And then we have these hot starts. For the second start of the engine, if the engine already starts, there is not enough time for it to cool down. The second start of the engine, 99.6% of the second start of the engine are hot start, and the other 0.4% need to dig deeper. They are warm, but maybe not fully warmed. Similar with the Volt, you have about 40% cold start, and then for the first one, the rest are warm. But the second start, in most cases, are hot starts. Now, do we have an engine start because we need more power, or do we have an engine start because the battery is empty and we're moving from electric drive to gasoline? This figure here is share of engine starts as a function of the battery SOC. And we have three cars here, the Volt, the C-Max, and the plug-in Prius. You can see that there is a kind of a zoom in the middle on this knee there. You see that for the plug-in Prius, 32% of the engine start were when the battery SOC was 0. The rest of them was when the SOC was higher than 0. Up to a 12%, we have this, a jump there. The reason it's like that is because the Prius is reporting it in a full units. That's the only reason. We get 1, 2, 3. We don't know more than that. And then above about 12% SOC, we have another 20% of the engine starts that happen at high SOC. It's similar for the Ford and for the Volt, but the much narrower SOC. We either have 0 or full. We can look at it here. The Prius, that's the power requirement at the bottom and the engine start distribution. The green, the red empty battery. The blue, full battery. When the battery is empty or almost empty, 5 kilowatt, you need a little bit of power, the engine will kick in. When the battery is full, you need 35 kilowatt, the engine will kick in. So it's still very low power, the engine will kick in. For the Ford, the battery is empty, the engine will kick in at 510 kilowatts. The battery is half empty, the green one, the engine will kick in at 20. The battery is full, it will kick in at 65 kilowatts, higher power, but still will kick in. For the Volt, doesn't matter if the battery is empty or half empty or full, there is no correlation between power requirement and engine start. Engine start because of SOC, not because of power requirement. That's what we see here. Where do we take it from here? There is much more analysis need to be done to figure out what is the actual impact of this behavior on criteria pollutions, on local emissions. I don't have it. So I think that we have a very simple takeaway point here. Larger batteries are doing way better. Larger batteries, PHEVs, larger batteries, BEVs. And you know, we were thinking that short-range PHEVs will plug in more. That's not the way it happens. Short-range PHEVs are not plugging in more. They're not compensating for the short range. Long-range PHEVs actually plugging in more. Blended PHEV have lower utility factor, limited both by the technology and charging and driving behavior. Longer range BEVs have highest utility factor on the household and the vehicle level, of course. And long range PHEVs may not have the cold start issue. The long range, not the short and middle range. Most of the charging events happen at home. Most of it. Any way you look at it, any number. Some happen at work. Corridor charging, long trip charging is still a very minor part of the story. And it's not just because these cars doesn't have the range, it's because that's how people use cars today in California. The ICEs, they don't drive much. An average household in California is doing 5 trips more than 200 miles in a year. So that's what we see. Longer range BEV can improve the environmental performance, of course, and future households may have you know, more than one PEV, and I think that's the next step. Because if we want to go to electrify the entire fleet, we need to start thinking about a BEV, PHEV, a 2 BEV household, and so on. I think that's the next step we need to go. As I said, we have many more papers that are using the data we collected here, and many more are coming. So that's just for you to look at, and I will stop here. Thank you.
All right, we have lots of time for questions. Reed, do we have any online questions in the room?
Hi, Gil. Thank you for that great presentation. So one of the big conclusions is that people are not using the DC fast chargers as much. Did your survey ask or try to figure out if people were more likely to buy a vehicle if there were DC chargers in their area? And even if they don't use them, is it still important to invest in that infrastructure?
This is very tough kind of question. So from the interviews, it's very clear that this map that showed that you can drive your car to New York with DC fast chargers is very important for people to buy electric car. I don't think that one of them will drive their car to New York on a DC fast charger, but this is something that people would like to know. It's adding value to the vehicle to know that it can do that. Same way that many of us buy a 4-wheel drive or buying towing capacity. My car worth more because one day I will need it, one day it will be able to do it. So that's the main thing. But that's not chargers around you. So it's a little bit different. I think that people, they less worried about DC fast chargers around them. And that's something they only learn after they have the car, that it's around them. But I don't want to kind of draw a conclusion for the main market. when we are going to more cars, more people that, more uncertainty, people that have different driving behavior, TNCs, multi-unit dwelling, and in general, you know, 2 cars per household and so on, DC fast chargers become more and more important. It's just a matter of time down the road.
My second question is, were you able to figure out if, especially for the plug-in hybrids, because I guess probably most BEV users wouldn't allow their cars to go to zero and get stranded somewhere, but do the cars really perform to what the manufacturers claim in terms of their electric range, or is that too difficult to tell from the data?
So this is the paper that that I said it is one of the 4, saying, yes, Californians driving faster than the utility factor, so the range is lower than what we expected. Also for BEVs, if you drive harder. But in general, I think that the utility, or the EPA range that we see in the US is what's coming up pretty realistic. Yeah.
Related to the prior questioner's first question, you, on one of your slides, showed the charging pyramid, but it appeared to aggregate all of the technologies together, BEV with fast charging, BEV without fast charging, and plug-in hybrids. How does that pyramid change, especially DCFC usage for individual technologies?
Yeah, so I do have some slides showing how much people are using fast chargers for kilowatt hours. And it was very clear that it's free, people use it quite a lot even. We got 25% of the energy for some cars that got free chargers were coming from fast charging. But do they need it? That's a very different question. In general, we see both for Teslas, Leafs, Bolts, new data, old data, that most of the charging, DC fast charging events happens around home, within very short range of quarter of the range of the car sometimes on average, and even less than that.
I have a quick question. It seemed surprising that I forget what % of vehicles are charged at the DC fast charger 5 miles to their house. Do you have any idea as to why? Did that come up in the interviews?
It was, yeah. It's where they buy milk or coffee. That's usually the story.
So it's the free chargers.
So it's a free charging, and it's usually correlated with other activities. Yeah. Mm-hmm.
Other questions?
It's not always free chargers. We have a little bit of DC fast charging that happened as a safety net when your charger at home was blocked by another car. Happens quite often when your workplace charger was occupied, or when you actually plugged in and you end up finding that the circuit breaker tripped and you don't have power. So we have charging, DC fast charging not far from home that add miles, and it's very important for the dependability of these cars.
So Gil, what a great data set, totally fantastic. So I'm interested in the data set moving forward. You kind of hinted that this was the earlier phase of the vehicles, and I was wondering if you could talk a little bit about how far into the future are you going to collect data, and what are the other types of vehicles we're going to see in subsequent research and publications and this kind of thing.
So now here, and this is where we are today. We will collect data a few more months from now, and that at least based on the second CARB project, we are on the last deployment, so we don't have another deployment. We have problem with the data that was supposed to be collected from cars that they were not actually showing anything, so we asked them to reinstall new cars. So we kind of keep rolling with it, just to try and get all of it from the Mirais and so on. But for now, this is where we stop. Tesla's only S and X, Prius Prime, Pacifica Hybrid, Bolt, Mirais, and we had the Volts and the Leafs. We don't have them anymore. So that's right now the end of it. I really hope that we will find someone who is willing to continue the study. it doesn't have to be, for example, a household, maybe just the PEVs, maybe a simplified version of it. But it took us a couple of years to figure out what we are doing, so it would be a kind of pity to lose it now.
I'm going to take a couple of questions from online. One asks, will the data collected in the study, such as EVMT proportion of total VMT for PHEVs and annual EVMT for BEVs, be incorporated into MFAC?
If it will be incorporated, that's not part of the project, but it will be at least on the cold start part. That was the goal of this part.
Yeah, no, part of this, the cold start definitely will inform MFAC. I know that they were very interested in this part of the study for MFAC. I don't know about the general EVMT component, so that's something we'll have to get back to the MFAC folks to ask directly. Another question is, what are your perceptions of the future market for PHEVs versus BEVs, and do you think consumers will continue?
That's a tough one. Yes, I do think that consumer will continue purchasing PHEVs. I'm not sure that how much the policymakers will keep support PHEVs. I think it's very clear to all of us that BEVs are better solutions. They are more elegant solution. You get zero emissions. You cannot drive it with emissions. You don't need to drivetrain and so on. But then you do need a lot of fast chargers, and it's hard to have 2 or 3 cars in the household BEV, even so I know a few people that have 2 BEVs household, but it's not that easy. So maybe PHEVs or fuel cells are a more suitable solution for the second and third car in the household. So when we try to electrify 100% of the fleet, can we electrify also 100% of the miles? And where do we compromise on trying to electrify the second and third car, people who live in multi-unit dwelling, people who live in rural area and so on? I think that PHEVs still have room over there. Different topic, we will have to find the right policy not to cannibalize one market with the other, selling PHEVs instead of BEVs. We need to sell BEVs first and PHEVs only second, I think, in the future.
So especially based on you mentioned that most households only take a couple of trips that are over 200 miles, and the breakdown that we saw in terms of the trip length by different type of vehicle, do you think that changes in the charging infrastructure that's deployed moving forward and those longer ranges is going to change how far people drive with these technologies, or are we going to see a similar breakdown of mileage and people might just choose the appropriate vehicle for that?
Well, let's put aside the 24 kilowatt hours leaf. When people were driving these cars, yes, once we get more range, we get more usage of the cars. When we go to 150, 200, 250 and north miles range, the difference in annual VMTs is starting to be just this tail of very few long trips, and we don't see a lot of difference in the VMT. It's mostly about matching your range to your routine behavior. And if you have a 150, 160 mile range car and every day you do 100-mile commute, you will have a lot of electric miles over every year. And that's where we see most of the difference. So there is a diminishing return on the EVMT, but the usability of these cars, the willingness to purchase the car, the number of times a year that you will need to find another option is much lower when you have a longer range.
Another question from the folks watching online. So this person has had a lot of issues with charger congestion. So they're wondering if your research team has gone out to see how busy the charging stations really are. Could it be that less people use DC fast chargers because there's not enough of them around? Too many people queued up and thus discouraging some of the participants?
That's a great question, and probably the toughest thing to do in social science or any of this research on behavior is to figure out what people are not doing. And what people are not doing in regard to DC fast chargers are a very tough question. I was trying to charge once. I was driving by the chargers. There were 2 or 3 cars there. I kept driving, and I'm never showing up there again. And we lost you in a way. It's really, really hard to do it. We are asking questions about congestion at workplace charging. We did ask questions about congestion DC fast chargers. And it's still just scraping the surface on understanding it. I think that the topic of charging infrastructure dependability is something very, very important if we want to get to the main market. I will put one plug into it. Pricing is a very important tool when we want a more dependable charging infrastructure. If it's free, it's first come, first serve. If you need to pay for it, you think about it, do you actually need it there, or is it just a nice parking spot? And there are other tools in making it more dependable.
All right, I have another question here. Are you seeing data from the Bolt that is similar to Tesla? Any differences of note?
Yes or no? I may kind of jump to conclusions on the data that we're still analyzing, but what I see with the Bolts is very long routine trips, very much like more than ICEs, because people who buy the Bolts usually have long commute and they have a need for an efficient car, and that's one thing. I don't see a lot of long trip as I have seen on the Tesla. And I think that it's not about the range of the Bolt, it's about the size of the car. What we did, a couple of studies showing that the long trips, people take the largest car in the household and not the most efficient car in the household. If they're doing long road trip, driving from Sacramento to LA, if it's one person with one destination, there is a good chance they will fly there. If it's 2 or 3 people with a couple of destinations, they will drive, and then they drive the bigger car in the household and not the most efficient car in the household, if it's a Prius or a Bolt. So if you have a Model X, you are much more likely to drive it to a 200-mile, 300-mile trip than if you have a Bolt. It's not about range. It's not only about range.
I have another question online if there's no more in the room. What type of data summaries or aggregation will be available for the public?
There's a lot of, again, there is what I want to do and what we can. I have a goal right now to start creating data distribution reports. So to take all of these different figures and create tables in a more aggregate way, and every couple of weeks to release one more report of the data there that can be useful for modeling and so on. That's not part of this project. And of course, no one else would like to pay for it, but we will start releasing more and more of the data. Right now, we will have this final report out in a few weeks, and that's what's out there.
In the survey, did you get any information about family income levels and see how income levels might be correlated with different charging behaviors?
Yes. It's not so much with income level. Driving an electric car is a very cheap thing to do, so we don't have much leverages with pricing. We do for sure see a difference if people live in detached houses with their own driveway and garage. They're way more likely to plug in at home. If they have solar panels, they're way more likely to plug in at home. And it's have some correlation with income, but not a direct correlation with income. If they live in multi-unit dwellings, they're less likely to plug in at home. Maybe another correlation with income is having free chargers at work. If they work for small companies like Google and Apple and things like that, they have free chargers regardless of how many people come with electric cars there. And we see a lot of our Bay Area sample that have free chargers at work and so on. But directly between income, it's there, but it's weak. We do have a good paper on it. It is out.
I have another question from the folks watching online. So it says, can you share more on if you collected data as to how and why consumers decided to purchase these vehicles?
Yeah, we used the survey to ask a lot of questions about the importance of incentives and the motivation to buy and so on. I think that every person you ask, if you ask directly, they have 2 or 3 motivations why to buy an electric car, and it's usually kind of the usual suspects. I want to be good for the environment, new technology, saving money, and so on. But in the end, it's have to make sense. It's have to make sense. It's all need to be on top of it. People like this, you know, they have this first motivation when they see a good car, and they cannot figure, if they will figure out that they pay more on driving that than driving their gas car, they will not buy it. If it's have big limitation, they will not buy it. If it makes sense, they will buy it. That's what Ken show us on his narratives. People buy these Model 3s now because it's new technology and it makes sense to them, even if they pay a little bit more. And that was kind of wish-wash. There's a couple of papers out there on much more details on the motivation, the impact of incentives, and so on.
The last question that we have from folks online was, what was your favorite finding and why?
I'm usually fascinated by when I'm surprised by the data, and I keep trying to torture it to admit that it's wrong, but then I'm deciding, okay, I was wrong. So I think that we're coming with the assumptions that if you have a short-range plug-in hybrid, you will try more to plug it more often to compensate for it. And we find that it's exactly the opposite. If you have a short-range plug-in hybrid and the engine starts anyway, you don't care, and you drive on gas. So that was something that we are carrying with us for a couple of years now. But it's still, I think, fascinating results showing that. But I will have the second, again, some big surprise for me. I did a lot of modeling 8 years ago, more or less, on where to put fast chargers when people are driving from here to there and stops on the way. And we were so wrong about that. That's not where they use their fast chargers. So that's my second kind of favorite finding there. When I'm wrong, probably.
Oh. Hold on. The question was, what was your least favorite finding?
Oh, what's my least favorite finding? I don't know what my least favorite finding. That's much harder. Yeah, it's when we don't have finding, when it's just a mess, and that's happens quite a lot.
Okay, we keep getting questions, but was there another question in the room? Is there a correlation between apartment dwellers or those who can't charge at home and the importance of DC fast chargers?
And should be. We don't see it in the data right now. We don't see it in the data right now. We don't see people who buy a BEV and don't have an overnight charging opportunity. It's not home. We should kind of be a little bit more careful and don't have overnight charging opportunity or a reliable workplace opportunity as their main charging location. Maybe it will happen in the future. It's not on our radar yet.
So what differences do you expect between the first and second generation? And do you think your analysis is starting to come closer to reflecting the common driver, or is there no such thing as a common driver?
That's a good question. I have to tell my CARB colleagues that I think that all of the money we spend on collecting data on 24 kilowatts-hour leafs is kind of a waste of time right now. It's an historical artifact. It's not something we should use. It's not the regular users. There's more than 100 miles is kind of the minimum that we should look at. And I think that you're absolutely kind of hitting the right point that what range is when we see exactly the same behavior as the regular drivers. And my feeling is it's the kind of around this 140, 160, somewhere there, people start behaving as the regular driver. But of course, it's a distribution. There is no one regular driver, and people that are far end of the distribution will need more range. It's a lot of self-selection that we have there.
All right, more questions from online, and I think these two will be the last. So these look like good questions. Which location for a level 2 charger, home or public, would you consider be the most cost-effective use of public funds?
I will put the rules, not the answer. When we install a home charger, for sure we serve an electric car. So that's an easy location to know. If you just purchase a long-range BEV and we help you put a charger, we know that this charger will be put to good use. So I think that's an easy one on that. But it will be used only by one car. If we put it in public and we make it paid, sometimes we can support 2 or 3 cars. So it depends on that. The other part of this answer is when people ask where, I ask when. If we have a lot of renewables in the afternoon, we would like to put more money into workplace chargers. If we have more access power overnight, we would like to put more money into home chargers. So in general, I think that we need to have better discussion between the energy modeling and the charging infrastructure location money that we are not doing a good job on it today.
If you could go to slide 48. This is a question about one of your conclusions on that slide. It says longer range BEVs have the highest utility factor, both in the vehicle and household level. But previous charts showed more household VMT on PHEVs and BEVs. Is it likely because they're newer vehicles of the household? Do you expect that longer range BEVs still have the highest household level utility factor for the case that in 5 years, it would still no longer be the newest household vehicle? And that they may even add a new, larger ICE to their fleet?
I think that it's a fair comment, and we need to do more analysis on what happened with. So we have. I think that the story of a Californian household or an American household is a small car, big car. That's usually the story. If your last purchase was the small car, your next purchase usually will be the larger vehicle. It's kind of a little bit, simplifying it, but that's the story. Right now, we have many more cars that can electrify, or many more options to electrify the small car, and very few options to electrify your large car. What is it like? You can do a Tesla Model X, a Pacifica, or maybe Mitsubishi Outlander, more or less. And there are few crossovers in the middle, but not really big. So I think that if we want to talk about greenhouse gases, and if we want to talk about electrifying the main market, we need to start thinking about how to electrify the second car in the household, and do it now before the guy will come to buy his second car 5 years from now.
All right, well, with that, thanks to Gil and the research team. And stay tuned for both the research report, which will come out in the next 2 to 4 weeks on our website, and then about a year and a half from now, the second version of the seminar with the newer vehicle technologies. So thanks.
Thank you.